Okay, we got session 12. We're going to talk about transpose and take it away.
All right, cool. Well, as always, please stop me if you have questions. Transpose is because there's the transpose descriptor. Transpose appears in lots of places, and it's also, yeah. So if I look for, say, just the core worker transpose, GB transpose, the internal worker. This, by the way, this grep string. Whoops, got that backwards. I'm very consistent with how I call my functions. Whenever I call my function, I always put a space and a left parentheses. And so if I declare the function or I talk about the function in some comment, I won't have the space paren. And so this will tell me everywhere I actually call the thing. Oh, I only call it in the 3 places. If I just do act GB transpose, you'll see it in maybe more places. Yeah, a lot more places. See where it's discussed or it's transpose.h and so forth. So, or, well, okay, well, it's different methods, sure. Um, uh, so it's importantly used in apply. So there's a feature of transpose I need to explain why I do it, because it's in, I use it directly from apply. So in apply, you can set the transpose descriptor, okay? Or you might be converting from an input matrix that's CSR to an output matrix that's CSC. So I have to do an apply of an operator and a transpose simultaneously. So what I decided to do is I created a method called transpose op, and transpose op does the transpose and it applies a unary operator. It's a fused operation because oh, actually it's in apply. Wait a minute. Where do I call it? Hang on. Where is transpose op called? Apply factory. Wait a minute. Um, hang on. Where do I, oh, yeah, there we go. Sorry, I just called transpose directly. That's it. That's it. So from the apply kernel, and I've got this oddly indented. This is just to help me keep track of what kind of operator I'm working on, because the and everything to do with that one operator, it's just as a helpful reminder that all those 3 are kind of stuck together. So apply can do multiple things, and so thus transpose must do the multiple operators. It must take either a unary operator or a binary operator with bind first or bind second and a scalar. That's what apply can do. It's a very flexible thing, how to apply an operator. And so this operator, so this is the worker code. This is the internal worker for GRB matrix or vector apply, because so I do all my error checks and so forth. And then finally, I do the work. Well, if the descriptor says to do a transpose, then all of the work of the to compute the temporary matrix for apply, okay, all of the work is done in GB transpose, which is the worker for the GRB transpose, but you can pass in the operator and the scalar, and it bind first, bind second if it's a binary operator. And so we talked about apply already, and I think we skipped over this transpose case because that's the transpose, but otherwise we did all of we looked at all of apply. So that's why transpose is kind of like both a transpose and an apply. If you look for the operator, it's going to be all over the place. Now the operator here, this data structure called GB operator, this is not available to the end user. My GraphBLAS now has lots of kinds of operators: unary, binary, index unary, and now index binary. I have 4 different kinds of operators. All four of those operators are the same struct in SuiteSparse, and I just have an opcode that tells me which one it is. So what I can do is then I can typecast all four of those operators: GRB unary op, GRB binary op, GRB index unary op, and now the future GRB index binary op. I say, fine, just give me the operator. Internally, it's just a GB operator. And then if I need to know what to do with it, is it bind first, bind second? Is it which operator it is? Well, I will be able to look at it and say, oh, you're a unary. Oh, you're a binary. And so that's the GB operator, because it's just the same struct, same content. Okay. So, and I think we probably, did we look at did we look at my operator struct contents?
I don't think so.
Okay, let's look at that. Okay, so this is this may seem like a strange way to define. I have actually, oh, sorry, I have 5 different kinds of operators. One is deprecated or historical. That's the GXP select op. That's been superseded by the indexed op. I have actually, and then I have the one that says that's all of them and all of the above. This is a rather strange way of defining a struct. I'll have to admit. It's a struct and then, oh, here's the content. Now the only reason I do that is rather unfortunate, but GraphBLAS has a ton of polymorphic functions, and those polymorphic functions are implemented in C with the generic keyword, which is ugly, so you always hide it in a macro, and it's like a switch case across the type of argument, right? Well, if you have 2 types, which are different names, but they're type def, like one is type def to the other. Like if I said, oh, I want to type def an int32 and I'll call it wonky. Well, you can't, it'll get confused. It'll say, well, type int32 and wonky, that's the same type. You can't have a different switch case. You can't switch on that type. You can't select one or the other based on that type because it's the same. The compiler knows it's the same type. So I have to fool the compiler. I say, yes, compiler, they're different. Look, compiler, this is one type and this is another type. Thank you very much. They happen to have the same thing, but don't tell the compiler that. Does it make sense? So I had to do that. So I have this is the content of all, I guess, 6 of my operators. Unary, index unary, binary. Now the new index binary, which is in beta release, and the deprecated select op, which is going away, which is historical. It's not used by anything anymore. And the generic GB operator, which is an internal thing. Okay. And I can typecast any of the other 5 into this one. So here's the contents of the struct. Every object, be it matrix, descriptor, semiring, monoid, you name it, starts with the magic number, which is important for detecting initialized objects. And it also has what's the size of this block of memory for the struct itself. And for most operators except for one, this struct is all there is, although there might be some other things I'll get to in a minute. In terms of names, let's see. Yeah. The next thing is that every object has the next 2 items in every object is a pointer to a string and the size of that string. And that's the user, I call it the username of a GraphBLAS object. You can set in GraphBLAS, any object has a GRB name that you can set and you can get. It's a feature I asked for, but it's a feature what I asked for is one thing, what I got was something else. So I don't use this GRB name. I support it, fine, there it is. But to me, it's just sugarcoating for it's not useful except for just that. It's just like, fine, you want to name your matrix, here's the name of your matrix, I'll let you name your matrix. I had wanted something else, uh, which is I need to know the name of the thing for the JIT compiler, which is what this is. This would be the actual function name because I need to stick it into my compiler. I need to stick it into my file, my function names, for example. You can't just put an arbitrary name there. I need to call a function with a name. That's the name I need. And that's not what I was given, spec committee. So I have both. There's two names to every single object in graph. Well, there's not two names to matrices because I don't need a JIT name for a matrix. Same thing is true. Well, now a monoid is different. I did not need a JIT name for the monoid because it's defined by its content. So a monoid doesn't have its own kernel name. Same thing with semmering. Same thing with the descriptor or a context, but they all have usernames. And you notice they all start with those four things: a descriptor, a context, a descriptor starts with the same four things. A semmering has the same four. And so what that means is there are methods. It says, give me an object, I'll tell you what its name is. Doesn't matter what the object is. So operators is the same way. Major, there's a type, the same thing. But see, a thing like a type also has to have the JIT name because I have to stick it in some code. And the same is true for an operator. I have to have the JIT name. So this is so then the next thing in the operator is the references to the three types, now four, because this is all new down here. And this isn't because I share, every operator has the same struct. The new things that the index binary op needed goes to every operator has this now, even though they don't use it. It's just null or empty, null pointers and zeros. But say a binary operator has output Z and two inputs X and Y. However, for a unary op, it would the Y type is null because there's no Y. For an index unary, the Y type is what I'm now calling the thunk or the theta. It's that extra scalar that goes to every operator. But for a binary op, binary index binary op, I needed another X, Y, and Z are taken. So these are for index binary, these are taken. Then I have function pointers. I have four function pointers because they're different types. So I just have all four. I could have done this as a void star and maybe have just one function pointer. I might end up doing that to save some space, but it's then easier. I don't have to typecast around and get confused by one function or the other. So there's a unary function, there's the index unary, there's a binary option, and now there's the new index binary operation. There's the JIT name if I have it, or 0 for built-in because I don't need it. There's the opcode, which tells me what operator this is. And here's the list of operators. Like here's the index unary operators. It starts at 52. The unary operators start at 1. Notably, the 1 op is 1. That's nice. Identity is 2 and so forth. These are the unary operators. And they all share the same opcode space. So the unary operators go here and then have macros to do the test. Are you an opcode that's unary? Oh, okay. And I can check to see if you're in that range. Are you an index unary? Oh, well, that's 52 to 71. And 71 is the index user defined one. Binary operators start at 72 and so on. It just keeps going. These opcodes are not special. If I add new built-ins, I will just have to change my codes, but nobody sees these codes except for me. So I can change these at will. And then I have this new thing called the which I didn't number sequentially. Well, I did. I put it in the middle, an index binary op, and there's only one of them. It's user defined. There are no built-in index. Sorry, index. There's no built-in index binary ops. There's built-in GRB binary ops that are now, I had before, first I, second J, for example. Those are now internally, those are indexed based upon an index binary op and a theta value. They used to have no function pointer because there was no spec for that. Now I do have a function pointer for them. So that's kind of handy. So this is the operator structure. I have to have a pointer to a variable size string for the whole C code for the function. Like, void star, z equals x plus y, semicolon, curly brackets, and everything. That's the whole function definition goes right there. The whole code for it. And then I'm also very, very conscientious in how I do my mess with my pointers. Whenever I have a pointer, especially in an object like this, I never just have a pointer. I always know exactly how big that space is I'm pointing to. So it's like I'm programming in Rust. I know everything about my pointer size. Okay, then I have a hash for the JIT. When I construct this object, I compute a hash code that I'll then also rehash to do fast hash table lookups. I don't have to go rehash everything about the operator. It doesn't change. Then the new theta, then the new index binary app. I know I'm going into operators in depth, but transpose is going to use all of this. Although transpose is not going to use the theta. Transpose is not going to be past this. And there's a reason for that. But let me just mention this while I'm here. So I have to add the theta value, the type, and also the void star pointer as well. I'm not sure why I put it in this order. This is kind of funny, but these are what I've got here. This is the type of that extra scalar for the index binary op, the function pointer for the index binary op, which is a different signature than these three. And then the scalar itself, this is like the monoid. See, the monoid is created, what is it created with? It's created inside a monoid is a binary op and a scalar called the identity value. Well, I add two scalars for the monoid actually, because I want to know with my monoids if they can short circuit, like Boolean, or once you see it true, you can stop and you can save a lot of computing time that way. I call those terminal monoids, and actually quite a few. Max on an integer, the moment, like max on int 8 or max on int 32, the moment you hit int 32 max, you can stop. So most monoids are actually terminal. Plus, the plus monoid is not. The max floating point monoids could be terminal, but they're not on. They don't stop at infinity. They stop at nan. Because max of infinity is nan is just nan. Max of nan with anything is nan. Nan is the terminal value of a floating point monoid. So that's not really worth having special code to check for nans and stop early if you see a nan. That doesn't happen. So I don't bother to do that. So that's my operator. And I'm going to use all of these but one in the transpose. I'm going to use all of just these. I'm not going to use this new one. And the reason there is that apply can now be passed three different operators to do a unary apply. Three different kinds: unary, index unary, and binary, bind first or bind second. And I decided that's enough. Apply is already 84 functions. Okay. We don't need another apply. We don't need it to pass in an index binary op and bind one of the scalars to some value and say, here, have fun. Apply it to the matrix. That's overkill. You could just as easily have done that with an index unary op and pass in a scalar or yourself that way. Okay. So there's really no need to do that. I didn't add that feature. It's just not reasonable. It's not worth it, because there if you're going to do if you're going to use a built-in index, a binary op like first I first j, well, that's already a binary op. You can just pass it in. That's fine. That works for historical reasons, but you don't need to, because first I, second j, and all that, well, they just translate directly to a unary operator that does the same thing. So why bother? I shouldn't have bothered to allow those to be passed in, but I do that. Okay, so historically, I did that in the past. So the operators are, GraphBLAS has a rich set of operators, and it's growing. It might grow further still. I have other ideas. But there's operators inside the transpose because of two reasons. You can do an apply with the transpose. Like say you want a complex conjugate transpose. I wanted to be able to do a complex conjugate transpose fast. Well, that's just an apply with the conjugate operator and a transpose descriptor. One line of code, one line call to GraphBLAS. I should be able to do that as a single fused operation if I want to do that fast. So do the transpose, and as I'm transposing the values, conjugate them to get that Hermitian thing. So that's why I did the transpose this way. That's one reason. And the other reason is for typecasting. Suppose another method decides that, oh, darn it, you've asked for the transpose descriptor here. And this is a case where I don't have an algorithm that can implicitly operate on the transpose. I must actually transpose the matrix. Now that's expensive. And if you look at the burble and this happens, this is bad news. You could have just passed me the transpose. Do it yourself, keep it around, pass it to me and reuse it, right? That would save some time, quite a lot of time. But you've asked me to do it, so I have to do it. So I actually make a transpose. And when I'm done with the operation, I throw it away because I have no place to put it. But since I'm transposing it, I might as well, if I also need to typecast the matrix for its subsequent use, well, the typecast is just a unary apply. It's a unary operator. So it's a transpose and apply an operator. So I need it there as well. And so the transpose will then take in like a identity operator, but identity with a typecast. Okay. So my point is there's a lot of hooks into the transpose code from outside the transpose method itself. There is a GraphBLAS method called GRB transpose. So I can start there. It's just called GRB transpose. It's a very simple method because all you can do at the user level is you say, here's my matrix and I want to transpose. There's no operator. There could be typecasting because you could transpose and cast. The type of ANC could differ. There is, of course, always the mask and an accumulator. But basically, then for the GRB transpose, I do my error checks. I have to make sure the dimensions match. Quick return if the mask is empty and complemented, which means don't do anything. And then I'm going to make a temporary matrix T, which is going to be the transpose. Now, this is a simple trick. I've done this for, I think I showed you this for the other things. I'll mention it here. Again, this will appear in most other methods. I have two ways of storing a matrix, by row or by column. And there's a descriptor that comes in. It says, please transpose or not. Well, that's 4 different combinations, right? 4 different cases. Well, I can't lapse those into 2 cases because once I get past my outer layer of the user code interface, all my computations are typically CSR, CSE agnostic, if you will. I use the word agnostic in my code. I said this is an agnostic function, act-l agnostic. It's going to be all over the place. Basically, I'm just working on a pile of vectors. I don't care which orientation they are. I pretend they're by column internally, and so it's this many vectors, or it's this long. Well, if you're doing a transpose, and I see that the input matrix is, say, CSE and the output matrix is CSR, they differ. That means if you've asked me to do a transpose, you've actually asked me to do nothing at all. Just make a copy because that is the output. Or if they're different and you've asked me not to transpose, but the CSR, and CSE formats are different of the input and output, then I actually do have to transpose the matrix. Does it make sense? I have to change the format from CSC to CSR. If you've told me don't transpose, but the input is CSC and the output is CSR, that is a transpose. Okay, so this is so if the input and outputs then differ, I have to it's like an exclusive or I have to negate the effect of the descriptor for the transpose. Okay, and now it gets worse. With transpose, if you set the descriptor to transpose, you get a double transpose and nothing happened, doesn't get transposed. So that's the spec. Okay, if you put in the null descriptor, you get the transpose. Okay, so if A is, it's counterintuitive. So, but if now A transpose is false, now it's an actual transpose. Otherwise, it's just a copy. There's no movement of data. In fact, it's a complete shallow copy at this point. This is order one time. It's a pure nothing. This is order one time, order one memory here at this point to construct this temporary matrix. Otherwise, I have to do an
I like that
actual
burble there
where
in
cheap.
the cheap. Yeah.
Yeah, it's a cheap burble, right? It's a very cheap transpose. And this is useful because sometimes it's you like you'll tell me to do a transpose. I'll say, yeah, that was free. Uh, I'm just doing a dupe at the end, maybe. So there's no actual transpose. That was a cheap transpose. And that's useful to know because, hey, that was fast. Well, I'm telling you, this is going to be good for you. You lined up the stars perfectly in your user code to get the cheap transpose. There's no actual transpose happening. Here, then is the transpose cast. Okay, so let's go to the transpose code. And how do I do it? Transpose with a typecast. I think this is a 4-line function. Yes, it is. Okay. It's just I'll explain this function on the left in a minute. So this is going to do the transpose and it's going to do the cast. And there's two different formats of it. If there's no accumulator, then I can typecast and transpose at the same time. And if I transpose into the let's see, into the final output matrix type. So I'm going to apply an operator to cast if I need to. Otherwise, I think I'm not actually going to do any transpose casting at all, but I call the same method transpose cast. Because I'm going to apply the operator later on, but I can't do the typecasting yet because there could be I have to do the casting later if the accum operator is present because things you're doing C plus equals a transpose. Some things in C will are bypass the accumulator, right? They go accumulator is a weird operation. EY's add is a weird operation. If you do C plus equals A with an accumulator, if A is the entry is A is present but not in C, it just typecasts from A to C. It bypasses the plus operator. And if it goes through the operator, then A must be provided as input to the operator. So whatever the operator type input is, there might be a typecast there and it's different. So every given entry will be cast in different ways. Typecasting with the accum has very strange behavior in GraphBLAS. And it's what the spec told me to do, so that's what I did. Ray has brought this point up that the accum is weird. The accumulator perhaps should have been done a little bit differently, because it's maybe it should have been a monoid, because it has this strange feature where you want it because of this place where it says, well, if you're in the intersection, apply the operator. If you're outside the intersection, don't do anything. It just falls through, but it falls through with typecasting from the input to the output. So it's
And
C equals C plus A with EY's add.
and Union avoids that, right? Because you're providing
The
the other
EY's union that I
parameter.
wrote,
Yeah.
the extension avoids that entirely. It always every output goes through the operator.
Yeah.
So this doesn't happen. And it's unfortunately it's too late to change how a QM works, I think, because it's such a so I've spent a ton of work for both conceptually and also code wise. It would just be a nightmare to change the accum, because what I've done over time is I've worked very hard to fuse the accumulation into each and every operation as I've been able to. Saves a lot of time. It's much faster that way. But that means now they're each wedded to the behavior of a cum, and assign is the worst. All of those 40 different kernels are written knowing about, they're written and designed for the behavior of a cum. And it's very different. If we were, it would change GraphBLAS tremendously if we try to change that. Anyway, so I'm transposing and casting, and the result of this is this T matrix, and then I'm done. But I'm not done. I now have the final accum mask phase, and every GraphBLAS method finishes off with the accum mask. This takes some output matrix T. It might be entirely shallow. This is the cheap one. It's order 1, but I have to run it through the accumulator, if any, and run it through the mask, if any. Now the accum mask phase is its own beast. That's in, I think, the mask. That's here. Yeah. That's another 1,500 lines of code. One of the things it can do is just C equals T. There's no accumulator and there's no mask. And in that case, it can just do an order 1 copy, a move from the input to the output. It can be very fast. So, but this is for another day. I'm not going to do a Q mask. Right now, the goal is to say, well, how do I actually do this work right here now? Transpose and do a typecast. Typecast, of course, is just applying a unary operator. So which unary operator is it? Transpose cast just binds me an operator. And the operator is actually just null for this use case. Null means, oh, Tim, there is no operator. All you're doing is typecasting. You're typecasting from the type of A. So there's, if you will, null is a placeholder that says use the right typecast function, of which there are 13 squared of them. Typecast int 8 to 16, int 32 to float, float to double complex, blah, blah, blah. There's 13 squared of these beasts. And I'll look them up later. I'll find the right operator. I have a switch case that gives me that operator. So, and you'll see a whole ton of these transposes. Okay. So that's the transpose cast, just picks the right operator and then calls the worker, the main beast here is CLOG is GB transpose. Okay, you can see here where I've spent. Okay, this is where the bulk of the work is going to go, and then it's going to pull in some templates and some current JIT kernels as well. So it's going to have three different transposings, depending on what kind of operator you're talking about. And so this one, since it's a unary transpose, it's going to eventually call this JIT if it needs to call it JIT. Okay, so finally we can get to the actual algorithm. We've picked the operator. We know what we're doing. And it can do this transpose. This is big. It's 1,000 lines of code. Wow. Okay. In comments, it's a big file. I may transpose using Builder. So we know how Builder works. I may, if it's hypersparse, this is the thing to do. Because I can't spend the simple way to do a transpose of a CSR matrix into CSC, for example, is to make buckets, one per column, and then go through the CSR matrix and stick things in the right buckets, count, and then do a cum sum, and then fill them. Well, but if n is 2 to the 60, you can't make that many buckets. So you can't, a bucket transpose is what I call it. You can't do. It's too big. So I will call the builder. It's doing the transpose and optionally doing either a unary op and or typecasting, and a null function pointer means please do the typecast. And the transpose can be done in place or it can be out of place. And if it's an in place transpose, I might be able to actually do it in memory in place. There are places in the code where I want to say transpose this matrix and do so as much as possible in place. Some of it's going to have to be out of place, but on the return, it's as if done in place. I've overwritten the input with the output on return. That's why this is going to handle all those different scenarios. So the input can have shallow components, which is even if in place, if it's the output can have shallow components as well. A shallow, like, a pointer to an array that owned by some other matrix. So this saves me some time and space quite a bit. The final outcome, whenever I pass a matrix back to the user application as a GRB matrix, they never have shallow components. I think I've talked about the shallow idea haven't I, with a GraphBLAS matrix object?
We've touched on it, but we didn't look at the moving pieces.
Okay, well, I could show you that really quick because the transpose is going to use this a lot. It's in the matrix type, built-in include GB matrix. This is the matrix data structure. This is the thing that holds the sparse, the hypersparse, the bitmap, the full, the FIBIX, right? It's got these different arrays. Where are we? Yeah, these five different primary components of 3 integer
Well, we
arrays of
did cover
Floyd.
this
Yeah,
in
we did.
in one of the earliest videos. I'm not
Yeah.
sure. We may have skimmed over the shallow copy parts.
So the shallow stuff is I've got those actually there's 6 pointers because one of them's a matrix, a GRB matrix. The hyperhash, we've not talked about the hyperhash. I don't think. The hyperhash is a matrix, GRB matrix, but it might be shallow too. So I have a Boolean flag, and I put it at the end so the struct is happy because bools are 1 byte each. So all my bools are at the very end. You see, this is the end of the struct here. I put my bools at the end, and then I put my floats, my 32-bit things, and I put above this are my 64-bit things. Okay, so it's a bit of out of order from logical order, but it's in memory order. So basically, these arrays or a matrix might be owned by another matrix, 2 matrices. Let's say I want to do a unary apply F equals maybe without a transpose. This is a simple case. Just C equals F of A. Well, that's C. If it goes back to the user as the matrix C, then it in the end can't have any shallow components. But internally, I might be able to temporarily, or at least, the matrix might not go back to the caller because it might have to go through the mask. It might be just a temporary matrix. So this output matrix can share the sparsity pattern to the input matrix. We don't have to make a new copy of the integers. We just have to translate the values from the input to the output. So in that case, X would not be shallow. This would be false. But the P, H, B, and I, the integers, would all be shallow, depending on what kind of matrix I have. And so what this is true, that means the matrix doesn't own that component. It's owned by somebody else. That's all I know. I don't know who. I don't keep track of who. Because I don't pass back this back to the caller. Basically, I have a shallow matrix. At the end of the day, the shallow matrix will be destroyed or made not shallow or whatever. But then when I free this object, when I free a matrix, if I see a shallow content, I don't free it. And that's all I have to know to do. So that's all I do with shallows. If it's shallow, I know I can't change it, but I never use it in a context. I mean, before I modify an output, I make sure it's not shallow. I make sure it's deep, basically. Okay, so I think at least three, let's see, I have three methods, maybe four methods to do the transpose. The transpose can be done like a bucket sort. The problem with a bucket sort is I actually have two forms of bucket sort, and they're both of them, neither of them are very parallel. Bucket sorts are not really great if you're doing them in parallel. You either have to have atomics or everybody has to have their own buckets. Atomics are not great for every entry. That's for every, incrementing where you go in a bucket. So parallelism is an issue with the bucket sorts. The builder is more parallel, it's more scalable because it's just doing an E log E sort of the tuples, right? You just fill in the tuples and sort instead of by row, sort by column or by row, by whatever to get the transpose. It's just a resort and there you're done. And then convert it back into hypersparse, say, after the builder builds a hypersparse matrix. So there you go. Well, and then it gets conformed later on to whatever format it should be. So that is a nice parallel method, that sort. The difficulty, it can take a little, well, no, it doesn't take more memory. But it does, well, it does it because you have to build the tuples actually. So it takes a little bit more memory. And if you have a single thread, it's slower because the bucket sort's linear time for, say, a CSR matrix. Not hypersparse. Hypersparse, I have to use the builder, but for a CSR CSC matrix, it's linear, it's order n plus e, where e is the number of entries and n is the dimension. And that's nice and parallel. I'm sorry, nice and fast. It's linear time, but it doesn't scale very well, parallelism. All right, so what am I going to do now? Let's see. So I'm calling this transpose, and I have now the output matrix and its desired type, the C type. And if this is ignored, is only used for typecasting, if there's an operator being applied, like doing C equals op of A transpose, there's three forms to using this. Doing the transpose with a typecast, or doing the transpose through an operator. If I do it through the operator, the output matrix type is the Z type of the operator. You don't have a choice. And I'll cast, if I need to cast later, I'll cast later. The input matrix, which might be passed in an alias to the C matrix, and then the operator. Well, the operator has now four things going for it. It's the operator itself, it's the scalar I'm binding to it, whether it's a binary, whether I'm binding first or binding last, and whether flip ij is happening. So flip, and it's unfortunate use of the word flip, I have to figure out a different name. The zombie, making an integer a zombie is, I also call it a flip, but it's not the same thing as this flip. The only thing that's similar is that it's a self-invertible function. The zombie is a function that's self-inverting. It's a function is its own inverse. It's like negate about -1. So it's a way of marking a zombie and back again. this flip of ij is a reversal of the row and column indices, like this. And I do this, I may need to do this depending on I need, because if I'm calling an index a unary operator, the operator is going to need to know it can't be agnostic to the rows and columns of the matrix. It needs to know, well, is I a row index, or is it a column index? Because is the matrix stored by row or is it stored by column? The data structure will hold one thing and the operator is going to need something else. So that's potentially to solve that issue, I may need to reverse the use of I and J. And that, if true, that's what I do. I'm going to reverse the role of I and J when I call the index operator. Okay. So I determine the properties of the matrix. I make sure that it is finished. The input is finished. Now this is a little bit different. Transpose is kind of handy. It doesn't actually care if the input matrix is jumbled, but in one case, if I'm transposing a vector, because I have a short circuit version for that, it does need to be weighted and sorted if that's the case. But transpose does a sort, or at least it doesn't care if the input's unsorted. It may produce a jumbled output. If I do a bucket sort in parallel with atomics, every thread is sticking an index in the buckets and it's out of order. It's out of order. Okay, so I'm getting the properties of the matrix, deciding how many threads to use. And then now I make my decisions as to what operator to apply. Okay, and there's 3 different kinds of operators already. First, there's no op. Okay, if there is no operator, then I guess if the output type is null, I forget what I use this for, but there's no typecasting. I'm just going to just do a plain flat transpose. Otherwise, I'm going to have to apply an operator. And let's see, if I have to decide with an operator present, I have to decide what output type I'm going to produce. So let's see, there will be no if the operator is identity, this is a special case, and it's in the right type, then I'm just going to make a copy anyway. So this is avoid the operator trick here, and don't bother to typecast. Otherwise, I have an operator being applied, and I may have a binary operator being applied. Okay, I may have a and this got to be too tricky, so I punted. If the operator is positional, or I call it internally, I call these positional operators. These are operators that have the indices that get passed to them. The index is unary op in particular. Or my special, like first I, second J, binary operators, which I allow here, unfortunately. That was a mistake. It just got to be too tricky to figure out what indices, how to handle the indices during the transpose, because this was also added after the fact. So instead of, if the opcode is one of these kind, I say, okay, I'm not going to do this. Instead, I'm going to first do the transpose without with no operator, basically, or the one operator. The output then will be ISO valued, so I don't actually touch the values. And then I'll do the values later. So I only have to do the values once anyway. Otherwise, if it's a user index unary op, it got really complicated, and I said, fine, I'm just going to wait and do the transpose and then apply the operator in place on the output when I'm done. It was just easier that way. So there is no operator and no typecast. Just cast A into the output and then apply the operator later. Okay. Next thing I want to do is I want to, now that I've settled on an operator, and I may have modified it above, now I have to decide, well, is this a transpose that's just purely symbolic? Because, I mean, if the output value, GraphBLAS has no symbolic matrices, but essentially I kind of made it so that they do. A GraphBLAS matrix is ISO valued, is one value that every entry shares. That's ISO valued, I call it. And then what this means is all the parallel work and all the movement of this data, it's just a pattern. I don't have to do the values. The values I do once. And so this is a function GB unop code ISO. This says, give me the code ISO is actually not just true or false. It's either, let's see, it's ISO, what is it? It's telling me if it's ISO valued, and if so, what kind of ISO-ness it is. I have a folder called ISO, GB unop code ISO. Okay, this is going to ask this operator, what's going to happen to your output, operator, please, if I call you? Will you, I guess I don't have to. Okay, do you depend on the indices? If you do, operator, no matter what, your output will not be ISO valued. So return, it's not ISO. Okay. If the operator says, I'm always going to return a 1, well, that's ISO valued, and it's special if ISO valued and the output is 1. Are you ISO valued, and are you a specific scalar, like the scalar I'm passing in? Any first or second of like first of X and Y is a binary operator, so it's going to be a scalar S. Otherwise, there's other cases here of isodness. I think there's 4 more. You're casting from A to C, and if it's identity, then you're ISO valued, but you're ISO with the ISO value of A, right? Casted to C. Otherwise, your ISO AC A is ISO valued on input, and if the function is not user defined, then I know what the output value is of all the entries of the output matrix is going to be in these cases. If it's like, take the square root, well, take the square root of all the values of A are equal to pi. So the output of C, every scalar will be equal to the square root of pi. If you're bind first, oh, it's applying the operator to the scalar of A and so forth. And this is op2. So there's like, this are just telling me which scalar to give to the ISO value for C, these different flags. And there's 1, 2, 3, 4, 5 of them, 6 of them, 6 ISO cases. 1, a scalar potentially casted, the A matrix potentially casted, go through the operator, and go through the operator. And there's 3 ways to go through these 2 kinds of operators. So there's like 6 ways of being ISO, and otherwise you're not ISO. So that's what I'm happening. That's what I'm asking here. And then, so are you ISO? If you're ISO, that's good. The burble is going to tell you that, because now we know that the output value is the output matrix is ISO valued. So that means I don't have to touch the numerical values of the output matrix, just one entry. So it's going to be a lot faster. Okay, so now finally I have the 3 different ways of transposing. First of all, I handle the empty case. That's easy. Just produce an empty matrix of the right type. Otherwise, I'm going to, and this is going to be 85 lines of code here, to do the bitmapper full case. And so I have, this can be a cheap transpose. Its transposes can be cheap in lots of different ways. The previous one you saw that was cheap was that T equals A, no matter what it was. That was pretty cheap. This is another kind of cheap. I actually have to do the transpose. But what if the input is just a vector? Well, that's easy. Yep, yep, there's nothing to do. Just pretend. It has to be a vector with no operator and no cast. If it's cheap, then that's going to be really easy. So now I'm going to allocate my output matrix. Let's see, what are this? It makes a new matrix, and what are these? How do these differ? Let's see. Oh, so this is a new, which doesn't allocate B or I or X. It's B or X because we're bitmap at this point. Okay. This has to allocate X as well. So I have to tell it, oh, it's not cheap. So allocate the output matrix contents of the full array. Okay. Then if it's cheap, it's just pointer tricks. No work at all. Just move the pointers around and flag them as shallow. Here, for instance, the T matrix content is a purely shallow copy of the A matrix. And if it's in place, I'm going to move the content from A into T because I'm doing in-place transpose on the T matrix. Let's see, how do I do this? So I'm ripping out, I'm changing the A matrix. So I'm going to rip it out and I'll put it back into the C matrix when I'm done. Okay, then finally, if it's cheap, that's one thing. If there's no operator, I call a method called transpose IX, and they're all called transpose op. So these are going to be appearing several places. No, I guess not. Transpose op. No, it doesn't appear. Let's see what happens. This is the apply. This is the row case. This is the general case. So I'm going to use the builder. Wait, that's it. Hang on. Oh, builder or bucket. That's right. Okay. All right. So from here to the end of the file, I have 1, 2. Whoops. No, that's the end of the work. Sorry, from here. From here, I have 1, 2. I'll back through these. Don't worry. 3, 4, 5. Yeah, there's 5 different cases. First one, the output matrix is empty. That's easy. Second one, A is bitmapper full. And to do that, I call one of these 2 methods I'll show you later. If I have a column, I'm transposing it into a row. That's going to be a special case. I have a row transposing it into a column. That's a very special case. It's just all shallow. But it's different if it's full versus sparse or hypersparse. And this is the general case right here. In the general case, I have 2 different methods, the bucket or the builder. So the transpose op, let's see, what is that? Transpose IX. They're not buckets. Let's see. Who calls this? I guess. Yeah, so the bucket transpose will end up calling this as well. So I'll get to this in 2 different ways. One is the bitmap case just goes straight in with no workspace. And the transpose op is going to do the same thing. That's right. I remember now. see. So the transpose calls it directly, or it's also called by the bucket transpose. Okay. So these are both bucket. Well, no, these are, hang on. The sparse one of this transpose op transpose as IX is the bucket. The other one is the full matrix transpose, and that's just in place. You don't need buckets for that. And you can't use builder because there's no indices anyway. So I'll show you these as I get down. We'll get down to them later below. They can handle any matrix format, sparse or full or bitmap or hypersparse. So how do I transpose a column into a row? Now I know that's a sparse column. I never have hypersparse column vectors ever. I prevent that. Nor do I have a hypersparse matrix that's n by 1. I never store that as hypersparse. Always store that in a sparse CSC format. So my GRB vector is always in CSC format. It's a column and it's never hypersparse, or it's either sparse, bitmap, or full. I've already covered the bitmap case. So now I know if AV dimension is 1, that means it's a CSC column vector. Well, it could actually be a CSR row vector as well. It's could be already starting out as a 1 by n row vector in CSR format. That'll also be never hypersparse. But I'm agnostic. I don't care what it is. Does it go this way or this way on the input? On the output, it's going to be reversed. That's why I put columns in quotes here. I'm thinking of it as a column. It might actually, to the user, be a row. Fine. So I'm going from this into this. Now, if all I had was, let's say, a CSC format to a CSC format, that's costly because that's an order n data structure for this row. If all I had was a CSR format and say on input, this was a column vector stored in CSR, that's also an order n space. That's ridiculous. But I might be then store vectors as a row vector. That would be nice. But then transposing it would be evil. I don't want to do that in CSR. So this is going to produce a hypersparse result. So imagine I have a column stored in CSC format. It's a sparse vector. I have a list of values and a list of indices. I can flip it like this. The values don't move, shallow. The row indices of the column vector need to become, did I say row? The row indices of the list of the column vector suddenly flip over. They become the H array of the row vector, the hypersparse. It's hypersparse, the 1 by n matrix. And I've got a list of their columns, which is the list of the rows of the input. And it's shallow. I go from I from the input vector becomes the H of the output vector. Isn't that cool? Hypersparse. All I got to do is fill in the P array, which is just 0, 1, 2, 3, 4, 5 up to the number of entries in that input vector. And I'm done. That's all I have to do. So it's super simple. And oh yes, of course I have to apply an operator. Dang it. If it's present. Or I have to typecast and the content. So fine, I apply the operator, apply that. Otherwise, it's the simple case. Otherwise, here input A, your input goes to T, and the values don't change. They don't move. This is order 1 work. Isn't that cool? This is super fast. Then look at this. That's the weirdest thing you'd ever see. The input row indices become the output hyperlist. Boom. No work. And if it's in place, it gets ripped out of A because I'm going to put it back when I'm done. Otherwise, fine, I'll just make a shallow copy. Input is this, output is a hyper sparse H list that's shallow, and it does not refer TH is shallow. It's owned, this array is owned by some other matrix. It's owned by the A matrix. But guess what? It's not the AH of the input matrix. It's the AI. It's the row indices of the input matrix. H of the output is a shallow pointer referring to the indices of the input vector, input matrix. Order one time. This is super cheap. It's just a parlor trick. But it's really important. This is a super important thing, because you can have you can transpose a 1 by n matrix. You can get a row vector. You can store a row vector in GraphBLAS, and you can extract a row from a matrix, for example. Get a row and you could get a vector, sure, or you can work with 1 by n matrices, or you might want to. Yeah, there's other places in the code, both LA Graph, where you're dealing with vectors all the time, and sometimes they actually get transposed. There is no, unfortunately, that's kind of weird. The spec says it's sort of two-faced as to when it comes to vectors. It says essentially that vectors have no direction. They neither go this way nor this way. They're not column or row. I think of them as row. Oh, sorry, column this way. And the spec says it's just a bunch of entries. There's no dimension. However, if you read the spec, it also says, what does, say, MXV does? What does GRB MXV do? Oh, it multiplies A times a vector, which looks like column. What does VXM do? If you read the spec, it says, oh, if you say like C equals VXM of AB, A is a vector, let's call it V times A, let's say. They write it down in the spec as, oh, that's actually doing C tick equals A vector tick times A. Because a vector is supposed to be, a vector is like this. And they write in the spec V tick. So it's a row times the matrix. VXM is a row times a matrix. Linear algebra. So they actually write that in the spec that, yeah, there's a tick there. There's a little transpose. Oh, by the way, this is now a row vector. We're telling you this is a row vector because this plain vector is a column. It's funny. Anyway, so this kind of thing happens. And so the similar thing happens. I'll brush over there from a row into a column. It's just the opposite. Okay. In this case, I have to allocate new space for the P array and the I array because it's of size A and Z. I have to build it, I guess. Oh, if it's not hypersparse. Yeah, if it's not hypersparse, I have to do some work. If the input row is a hypersparse row and I'm trying to produce a column vector, then it's the opposite of the thing above. Because the thing above is taking a sparse vector on input and producing a hypersparse vector on output. This input row might, if it's already hypersparse, then it's the opposite of the thing above. If it's not hypersparse, if it's an array of size n, basically, then I have work to do. And so I have to do that here. I either, if the input is hypersparse, then it's just the opposite of the quick thing above. Otherwise, I've got to walk through some order n space and do some work. And I don't do this. Oh, this is the single threaded version. And or I can construct it in parallel. I have to go through the pointer array of the row vector, row matrix, if you will, 1 by n matrix, find out where the non-empties are and make a list of those indices. And so then I do it in parallel here. So the first pass is, this is a very common process in GraphBLAS and a parallel sparse algorithm. The first, and stop me if you have any questions. I want to say too, the first pass is a count. Every thread counts how many it has. and then it's a cum sum across the tasks, and then it's do the actual work. It's a 2-pass algorithm. And I finished this parallel algorithm with this sequential algorithm in debug mode that asserts that I got the same answer. This code right here is the same as this code right here, because this is simple to understand. And so I do the parallel work and I make sure, yep, I actually got the right answer if debug mode is on. So I check myself, I check the parallel algorithm with the simple sequential algorithm to make sure that I got the right answer when debug mode is turned on, which is terribly slow. You have to edit the code to turn this on. And that's it, just some cleanup of the finalizing the data structure. Now we get to the general case, and it's 12:30, so I still have time. Okay, now I have to decide what I'm going to do. Do I use the call builder, or am I going to use the buckets? And if I'm going to use the buckets, I'm going to be returned here in this method called GB transpose method is making this decision. I have these methods called method. And what they're doing, all these methods are doing is deciding what other methods are going to use. They're just a chooser, a heuristic chooser as to, okay, tell me what you want to do. Some of them are pretty complicated. Some of them, for instance, let's see, I'll show you here. Cloc by file. Some of these are super, you know, deciding which matrix multiplier, which assignment you're going to use is really complicated. EY's methods are much faster. The transpose is pretty short. So let's decide which transpose method we're going to use. Transpose method, this is what we're calling. All right. There's some really funky heuristics in here. Bucket factors I'm computing. Okay, these are highly tuned, and for a different machine, this tuning might be off. But I spent a lot of time figuring this out. So I have a sparse or hypersparse matrix to transpose, and I can do it one of two ways. I can use the bucket method or builder method, and that's all I'm going to return true or false. And I don't know if and also if it's I'm going to choose between, I'm going to return the number of threads I'm going to use for the bucket method. I may have 2 threads available, but I may decide, I need to use an atomic method. I've got 2 threads, but you know what? It's not worth it. I'll use 1 thread instead. I'll use the sequential method. So the builder the bucket method, there's 3 internally. There's 3 kinds of bucket methods: sequential, atomic, and non-atomic. And the non-atomic methods don't need workspace. So that the decision here will be, if there's no workspaces allocated, or number of slices for the workspaces, this is an integer, then you'll use the atomic method. So the output is more than just a bool here. It's deciding the algorithms to use, up to like 4 different algorithms, whether I can use atomics or not, whether I'm going to use, and it whether I'm going to use, if I use atomics, then I'll use 1 bucket, 1 workspace. If otherwise I need 1 per thread. How many threads am I going to use? I might go up here and decide, where's n threads? And I choose, now I'm choosing, like, as the problem gets bigger, builder gets faster, I've noticed. And so 1 is linear time, 1 is a log a, 1 is a plus m plus n. So I have this fudge factor that's growing as the problem size is getting bigger. And then I estimate, see that the transpose is linear time in the buckets, but it's linear in the number of entries, the number of rows, and the number of columns times the fudge factor. The work of the builder, on the other hand, is always E log E, where E is the number of entries. Okay. So I want to know which is going to be faster, basically. And there's my estimate of the work that each of them are going to take, and then I'll choose the one that does the least work. Now, what's interesting about these two tests here is that if the matrix is massively hypersparse, the dimensions of the matrix are 2 to the 60 or something. Huge, ridiculously huge. Then one or both of these numbers are going to be massively huge, 2 to the 60. So I'm always going to pick the builder. And there you go. And everything else, like if it's sparse, well, okay, now you're somewhere in the middle. Do you want to spend E log E time, or do you want to spend order N plus E time? If it's sparse, maybe the buckets are fine. Unless the matrix is getting big, in which case, when the matrix starts to get really big, well, then you're gonna kind of want to start using the builder instead. So the fudge factor goes up. This is just experimental. I'm sure, like I said, the thresholds are going to be different on different machines. I tuned it for one machine. It seems to be fairly robust, but you know, who knows? So that's the decision. If I use the builder, then all I got to do is really just do an extract. I have to get the column indices of the matrix. If I look GB extract, every row and column, every row of every entry in the matrix has an I and an X. It doesn't have a J. It needs a J. In other words, I'm doing part of the work of extract tuples, getting the tuples into this workspace. And this is going to be the row, these are the column indices of the input, the row indices of the output. And so I'm building this output matrix. I need the row indices. And I can decide whether or not I can reuse some memory spaces or not, or have to allocate new memory spaces. Same thing with the row and column indices, the indices. Do I need to do a mem copy or not? Can I do the build in place? I can recycle the indices. Do I need to typecast or not before I do the build? So I do it now before I do the build. Then I call build. Now when I call build, some of these, I think S work, see the inputs to this builder, I think I described, could either be given by S input, which is array you don't modify, or S work that you can modify and free when done. So there's two ways of providing the triplets to the builder. Either workspace I'm going to consume, or values I'm not going to touch. Well, I guess the row indices, the column indices, I always consume them. But here, I may choose one or the other. And I think it's the choices up here. Like here, I'm going to be using the input matrix data, which I don't want to touch because the input matrix has to be preserved. Here, I don't care. I'm going to use, S work is null. Where do I set S work? To be null. Oh yeah, right up here. I should have done it down here as well. And here, I'm going to write to S work because I have to apply an operator, but I'm going to throw it away when I'm done. So this is consumable space that goes into the output matrix. It gets moved it's moved into the in order one time. I don't have to apply the operator and then copy it into the output matrix. So the builder will handle all that for me. I've already done that. And there's no duplicate operator because there won't be any duplicates. There's no duplicates in the input matrices. Or I do the bucket sort and it's 1238. Okay, I think I have time. And then I have to do the transplant, sorry, input into the output matrix. I'll get to this bucket now in a minute, transpose bucket, which is a big piece of code. And then finally do the last work is if I had a user index operator or positional operator at the very end, now I apply the operator here and move the values. The values have been computed. Now it's been transposed. Now I can apply the operator, it can depend on the indices, and I don't get mixed up as to what I talk about the row or column and so forth. And I just couldn't figure out how to do it otherwise. I'm sure there's a way of doing it as I go for the user applied operator, but I didn't figure it out. So I just punted and did it as a 2-pass method. Okay, because it's not going to be too common to do a transpose with it. A transpose with a user defined index unary operator. Okay. You apply an index unary operator, but you also want to transpose at the same time. Yeah, never mind. I won't do it at the same time. So let's go to the transpose bucket. And there's templates for this. Okay, no, there's not. Sorry. These other methods are so transpose bucket. Oh golly, this is a big line. I'm not sure we're gonna get to 1 o'clock here. So now I'm committed to do the bucket transpose, and I have already done. I think I've got workspace already allocated. No, I've told myself how many workspaces to allocate. I'm going to allocate them here, and there we go. I allocate all my workspaces, each of size like the length of the vector. Okay, so this could be expensive. If you're an atomic parallel bucket transpose, you just need one workspace. This will just iterate once. If you're non-atomic parallel, every thread needs its workspace, and that's what that will do as well. If you're sequential, I don't think there's any workspaces. I forget. Okay. The transpose. Phase 1 is a symbolic analysis. I have to, I slice the A matrix into pieces. I slice the work by I slice the vectors of the input matrix, I guess. P slice, I call it. So it's producing an array of boundaries as to where the threads are going to work. If it's one thread, it's easy. I just have to first sum up the number of entries in every row because that's the size of each bucket on output. So it's going from a column matrix to a row matrix. So I need to count how big is each vector of the output. So it's just a very simple 4-line loop, 5-line loop. And then cum sum, mem copy, that gives me the column pointers of the output, or the row pointers, if you will. I'm writing this as if I'm producing a matrix C that's stored by row, because it's row count. So the input matrix produces the CP array of the output, which is now effectively stored by thought. I can think of it as a matrix stored by row. If there's one workspace, so otherwise, this is sequential. One thread, no buckets, no works. Oh, there is one workspace. Sorry, I need one workspace. Otherwise, if it's parallel with one workspace, that means I'm doing parallel atomics. Okay. So I do an atomic update on the workspace. So multiple threads can each touch a row index, the same row index. So every update, every workspace increment has to be done atomically, and that's kind of slow. Otherwise, the rest of the work is the same. So this is just phase 1. Non-atomic method is fairly more complicated, but every thread has its own workspace here. And then the next phase, this is very expensive. We have to sum to decide how many entries are in every row in the output. And we have to go through every row and sum all the workspaces for that row. Then we can do the cum sum. And then we can do a reverse cum sum, I guess. We need to push this back to each workspace to tell each workspace, each thread, where to put its piece of each row. Every bucket has been chopped up into one area per thread. Oh, this is tedious. But this works pretty well if you have a small number of threads. It works very well. It's very fast. And it's modestly parallel, right? If you have a few number of threads, it's better than the sequential method. It takes a lot of workspaces. You can't do 100 threads with this. You have 100 N workspace. That's really big. And then I do the actual numerical transpose, and this is the final stuff here. Now I have the phase one, phase two. Now you've seen this before, these two methods before. One of them is doing the operator, one is doing just the values and typecasting. Let's do transpose op. So this can now handle sparse, hypersparse, I should say as if full, sparse, hypersparse, bitmap or full. Okay, and it's using, now it's using, it's a bucket. This whole thing is the bucket. Where is it? This is the bucket. Yeah. This is the bucket transpose. Apply bucket and apply an operator. And there's several cases. I may have an operator, a unary operator, in which case I have the factory cases, switch cases defined. Let's do the apply the unary operator factory, and let's look at that. And that's actually in the apply space. Okay, apply factory GB unob factory, because I have to apply. This is the switch case for all the operators. Okay, and so that's from apply, but the worker is doing a transpose. Else I call the JIT to do the same thing, or I call the generic case. Now the generic case, the operator is of course very expensive. It's a function called a typecast. The input to the input to the A matrix, the input of the worker, I mean of the operator, and then the operator. And the matrix is of type C of the operator. So this is now back at transpose. This is transpose. Let's see, this is the template. GB transpose template. And it's going to call then 3 subtemplates, bitmap, sparse, bitmap, or full. And I think, yeah, there's a test here. If it's a JIT kernel, I know at compile time whether I'm doing sparse, bitmap, or full case. Otherwise, I have to ask at runtime. There's all 3 algorithms are sitting here. The full and bitmap and sparse or hypersparse case are done in three different kernels, 3 different templates here, which are sitting here inside template folders. So let's look at these right now. So I'm going to call whoopsie template. Let's look at these templates. So bitmap, this should be faster. I really need to do this. This is the stupid transpose of a full matrix. It's the bitmap transpose, but it's a stupid method. You know, if you have a dense matrix, there's better tricks to transposing than just the childhood, you know, childlike AJI equals AIJ, iterate over I and J's, right? It should be done by chunks, tiles, and so forth. But I just haven't, you know, I've run out of steam. The bitmap case basically just says 1 task per thread. Give me a chunk of the matrix. Figure out where I am. Divs and mods. That's not very nice. And then ask, do you exist on input, where if so, that's where you exist on output. And if you exist, apply the operator. So it's literally doing iterate over all the, actually it's iterating over the output matrix one in stride one, and grab the output matrix. It's also a bitmap matrix. Grab it somewhere and move the data. So this is not a great algorithm. The full is also equally evil, just no bitmap. Okay, divs and mods and everything. It's not even, it's doing div. The reason it's doing divs and mods is because then that makes the iteration simpler. It'll just iterate a bunch of entries, not to figure out, iterate over individual rows and columns. I could just iterate over the whole dense matrix and then use div and mod to figure out where I am. That's not so great. So these two methods I'm not happy with, but they work. Okay, the sparse is very different. There's three methods here now. This is the core three methods of the transpose. The sequential method is super simple. Iterate over the input matrix. Iterate over all the vectors of the inputs. Get its GBH of S. What the heck is that? S matrix. Okay. Well, get the hyperlist, find out like who are you, the kth vector. If you're sparse, then this is J is equal to K. Iterate over the entries in the column of K of A, and then do the work, right? Figure out what's the row index, put you in the bucket, and apply the operator, unless you're ISO value, in which case don't touch the numerical numbers. Okay. If on the other hand, you are you're parallel. There's one thread. If there's multiple threads with one workspace, that means we're doing atomics. We're going to do the same thing. We're going to slice up the vectors. I'm not slicing, it's a simpler slice than many of my methods. Every thread gets a chunk of the input matrix. Columns. I'm not dividing up columns here. I mean, one thread does a whole column right here. And it's basically doing this work atomically. Get the workspace incremented and assign it to PC, but do so atomically. So it's the same algorithm as above, except I've divvied up the vectors of the input matrix. So that this part is different than this. This is just one thread goes across all the vectors. This is divvy them up. This part is identical. So the thread now is working on one vector. And then this part here is almost identical. The only difference is this thing here must be done atomically, and it's done like that. And unfortunately, because Microsoft Visual Studio's compiler is a piece of garbage, I can't just write OMP atomic or whatever, do it, atomic capture, because they only support OpenMP 2. So I have to have a macro that hides how to do that atomic increment and capture. It's called atomic capture. Piece of garbage. But otherwise it'd look like this with a decorator on top that says, please do this, GB atomic OpenMP Pragma OMP atomic or something, and you'd be done. It looked just like that. But no, I have to write this ugly garbage. Oh well. Then finally, the non-atomic method. This is easy because every thread has its own workspace. Every thread knows exactly this loop right here, this work, this work, that's the same as the sequential algorithm. But every thread just has its own workspace. If you look up above, this algorithm with the one above it, look, let me see if I can template. What is this? This is GB transpose sparse. It's going to complain. There we go. Here's the sequential, and here's the parallel with workspaces, no, non-atomics. It's identical, actually, except that the thread T has its own workspace and it works on its own vectors. Otherwise, now this is the same. And the reason it's the same is because the position in the workspace has been shifted to the point where this thread knows where all its pieces of its buckets are in every output vector. So that's why this code here, and actually this entire piece of code is now absolutely identical to this right here. The sequential case. So this method is, is very, it's in a sense it's more parallel. The non-atomic method, there's no competition over atomics, but you need a ton of workspaces. And so as the number of thread grows, this method just hopelessly does not scale. And as the number of thread grows, this becomes better, but then you're dealing with lots of atomics. So eventually at some point it says, well, forget the atomics. Let's just do the builder. Let's just do sort and don't use any of these methods. Okay, so that's the transpo. Let's see, let's me quit that. So that's the algorithm. I'm almost at 1 o'clock. Let's see. Where was I in? Transpose op, I think, was the one that was doing all this different work. I think I was in this method, yeah. So that's what the unary worker is going to do, the generic kernel is going to do. I may instead be applying a binary operator. Again, I have factories to do that, but the switch case is different. It's a totally different set of operators, but the different JIT, and there's the generic will be one generic, I think, for both, if I recall. There's factories for the bind second. There's a JIT for bind second, and then there's a generic case, which is going to do either the bind first or the bind second. And for some reason, I decided to put them both down here. They're also going to use that same template, though. See, all these different algorithms, all the JITs, they use the same algorithm. It didn't look like there was a binary operator here. Say this one. It's just apply the operator. What is it? Well, if it's bind second, this macro just hides all that stuff. It's just whatever. I have a scalar, I stick it in a binary operator, and I have an input matrix, and I apply the operator to the input AX of PA, and it produces CX of PX. It's all templatized away. So this line of code handles a unary operator. It handles any typecasting. Typecast can do this too. Same set of algorithms, but that's now a typecast. Binary operator, bind first, binary operator, bind second. It'll do them all. One algorithm. So this is templatized across all those different ways of doing that operator. And if we look at the factory kernels, for instance, if we go to the factory kernels, let's pick, I don't know, square root. Why not? You want to transpose in square root? Great. There's your. So what do you do when you take the square root? Okay, there's the operator. Get the scalar and apply the square root, which is square root. Okay. And transpose is in here. Transpose, it's going to be, there's the transpose and take the square root. I have tons of this. Applies the identity operator, but say this one is going to typecast between uint32 and f and float. So here the unary operator is a typecast. Otherwise, it's the same. I have identity operator is burst. It takes the role of the typecaster. It's identity, but it's the input and output types differ, so it's a typecast. The other operators you have to precast. You don't. I don't have lots of variants of those. It would just explode if I did that. They always have, pretty much always have the types, input output types the same. Like, you know, take the absolute value of an N16, produce it in 16. I don't cast that at the same time. I could. The JIT could. It could produce way more, but I don't exploit that. So I think, and let's just look at one of these JIT kernels. Let's look at bind second JIT. Why not? Look at source JIT wrappers. Let's look at GB transpose bind second JIT, let's say. Okay, so what do? Say the code looks identical here. It's always just encodified and element-wise algorithm. It's element-wise, it's not unary because it's a binary operator. I have to encode a binary operator, and then I JIT it and call it. And the kernel I call, I'm passing in these workspaces. See, these workspaces I've already allocated, passing in the operator to encode. The JIT kernel doesn't take as input the operator because it's encoded in the it's compiled in, it's baked in. If I go to and look at some of these examples, I wonder if I have these built. No, I don't. I could see if I could compile my code really fast. I might have to compile them. You could see some of these in action. Might take a while. So let me go to, it worked. Okay. Oh, cool. I've got them here. Okay. 4,000 JIT kernels. Oh yeah, my laptop is compiling GraphBLAS. That'll take a while. Okay. I have 696 bind to, some with apply, some with transpose. Let's just pick one. Here's one. Transpose and apply an operator that's a binary operator with a scalar bound to the second operand input. What is this? What is the, oh, it's exclusive OR for whatever reason. And exclusive OR, where the output, oh, that's interesting. It's logical exclusive OR, but it produces a true false, but I'm casting it back to UN64. Okay, so that's what this operator is doing. And that's the binary operator. But when I pull in the template, I'm going to kill this because it's going to take too long. It's the GB JIT kernel transbind second CD source JIT kernels. And it's going to be, let's see, it's going to be in the template folder. Yeah, these are all my JIT kernel source codes. So I've got 40 of them ish. JIT kernel transpose bind second. Where are you? Here we go. Oh, that's boring. Okay, all it's doing is it's saying, but this is not boring. That transpose template, we just saw it. That's the algorithm, but we're defining what it means to do apply. What does it mean to do apply? Well, it's to do apply means get the entry of the A matrix and run it through an element-wise operator where there's the matrix entry, there's the value Y, which is the scalar. This is the bind second. If I look at the bind first, it'll look just like this. Oh, too many kernel names. There's bind first, there's bind second. Bind first, bind second. They're identical. I guess I've got it undefined for some reason at the top of this. Otherwise, you see there's a scalar, there's the matrix, and same algorithm, different prototype of the function. I
They're
have to,
backwards in the other one, right? It's AIJY and XAIJ. Did I see
yeah,
that right?
it was right
Okay.
here. Yeah.
Okay.
If
Yeah.
you, if I do a diff between the two, that'll be that'll be more clear. Um, the declare is different because you're getting the bind first. The value is passed to as the B, as if it were the B matrix. So I have to declare B because that declaration will declare a scalar of type of the input for the second operator. And then the get will do the typecast of the input matrix to the type that B must have to be passed here if it needs to be typecast on input. And then it calls the operator, whatever that operator is, it's compiled in. That EY's operator is basically, oh, it's right here in the compiled template. It's the binary op. What is the binary op? Exclusive OR. An exclusive OR bind first, exclusive OR bind second. Same kernel, same include template, same template on the inside. They're not, they're identical. Just the definition of the operator is different. So that's all the way down to the JIT level. And this is, you know, saying, okay, all the types are uint 16 and there's the exclusive OR. And since it's not an EY's add, I guess I don't define these. Copy from A to C and B to C doesn't happen unless you're an EY's add. So these are empty and I don't use them even anyway. The input matrix is sparse and this is how I access. I think I've shared this with you all before, right? How do I get the content of the C matrix? If it's sparse, well, it is sparse and it is not the other three. How do I get the P, the H, the I, the B? Oh, well, here it is. This is how I get the hypersparse. The kth vector is the kth column of the matrix. How do I get the row index? How do I get the bitmap if I wanted it? I don't have to say, oh, are you bitmap or not? I can say, give me the thing in the bit. Is the bitmap say yes? Well, yes, it's always there. If you're sparse, if you look at an entry, it's always there.
Yeah, we covered that. We
Yeah,
did the JIT compiler
we
pretty
did the
early.
JIT. Yeah, we did the JIT. And so, it's templatized, it compile time to death. And then finally, at the very end of the day, the final kernel is just that. It's one of those little simple 3 loops and we're done. Or it's the bitmap case, full case, or 3 sparse cases. So it's 5 algorithms, I guess. It gets kind of difficult to say, well, how many algorithms do you have to do the do X, Y, Z, do the matrix multiply, do the transpose? I don't know. I guess I think I have, how do I count? I mean, I lose track of counting. I guess I have 3 buckets methods: sequential, atomic, non-atomic. For the sparse case, I have the bitmap case and the full case, which are mediocre, but they're parallel, but they're not so great. So that's 5 algorithms. But then I get the builder as well. That's 6 algorithms. But then do you count those special cases of the row becoming the column becoming a row or not? Yeah, so that's 2 more. Is that 8 algorithms? I guess that's 8 different transpose algorithms. But then each of them handles unary. Well, some of the, for applying an operator doing a typecasting, they handle, bind first, bind second, unary op, index unary op, blah, blah, blah. Well, they don't handle index unary op. That's always done later. So it's just mix and match. How do you count them? I don't know. So I think that's transpose. This is the number of JIT kernels that I compile in my exhaustive test suite. That's what 4,000, number 4,000 is, 4,000 kernels out of, so. Let me see if I've hit, it's a little after 1, so to finish up really soon. I think I've got all these except there's a thing called transpose. I've covered transpose cast. Transpose in place, I don't think I've seen, and that's that. That's easy. That's just makes my life a little simpler to remember how to transpose a matrix in place. I don't have to, pass in all the different. And it happens a lot of places. Like get set. You tell the matrix, hey matrix, you want to change from CSR to CSC. Okay, I'll do it. What is that? That's a transpose, but it's in place. Import export has to do it potentially, because what if you wish to unpack a sparse CSR matrix, but the matrix is actually in CSC? Oh, you've asked me to do a transpose and then unpack it for you, because you're wanting the output in compressed sparse column form and it's in CSR. So I must transpose and then give it to you. That's expensive, but that's what you asked for. So it's not a good idea to ask for that, but I'll do it. So, the pack unpack is a good place where the other things that, like, what if you say unpack, it's a CSR, but it's not in CSR. It could be bitmap, it could be full, it could be hypersparse, and I could convert it. So it's very useful when you're doing pack unpack to say, well, before you call a method to unpack it in a format you're asking for, ask me what format it's in. And if you are happy with that, then I'll just give it, you just call that particular pack unpack method and then, or unpack, and then it'll be free. But if you can only tell you say, I want the matrix and I have to have it CSR format, no other, because I only want to handle it in one format. Well, then fine, do it, call it, but I'll have to convert it. And one of them is a transpose. So that's expensive. So, that's the transpose in place. I think that's it. Yeah, that's everything. A lot of, oh, sorry, I don't have the CLOC here. This is a new machine.
Well, it seems like we hit a
Yeah, I
stopping
think
point on
we're
the video,
done.
right? Yeah.
I think we've basically seen, yeah, transpose, whoops.
Well,
So
I guess,
you've seen
go
how
ahead.
tightly coupled the apply and the transpose are though,
Yeah.
too. That's really important. And the transpose is elsewhere used so many other places.
Every descriptor could potentially
Yeah,
invoke
right.
it, deep or
AXB,
shallow. Yeah.
MXM, if I need to, there's several places I need to transpose the input matrices.
Okay. Well, I'm going to
So.
stop now.